Today we'll show you how to spot weld aluminum, specifically spot weld nickel strip like this to aluminum battery terminals, like this battery, and this battery. A typical battery like these 18650 batteries here, the battery terminal is usually steel or nickel plated steel, so you can easily weld a nickel strip on it, or you can even solder on it. You can see here I put some solder on it on here and also on the bottom, and it's very easy to solder or spot weld. However, there are other batteries that have aluminum terminals, and you cannot spot weld onto these aluminum terminals. This one here is a lithium iron phosphate battery prismatic cell, and both terminals are made of aluminum. This is a Tesla Model 3 2170 cell, and the positive terminal is made of aluminum. The negative is steel. This one here is a pouch cell. It's made by LG Chem, and it is salvaged from an electric car. The positive terminal is aluminum. The negative terminal is copper, but it's plated with nickel. So on this side, on the copper side, you can easily spot weld or even solder on it. On the aluminum side, it's a different story. You cannot spot weld or solder. Aluminum is a very difficult material to work with. It's very hard to weld, and it's nearly impossible to solder. However, I have cracked the code of how to spot weld to these aluminum terminals, and I'm going to show you that today in this video. I got a piece of scrap aluminum here, and I'm going to try and weld my piece of nickel strip on it. First weld, and let's see what we got. See how pathetic that is. Extremely pathetic. Now let's try this again. And this time I'm going to put it on this side of my piece of aluminum. Here we go. Alright, see what we got. That is a good weld. There we go. Let me show you the back of the nickel strip here. You can see the remnants of aluminum that is melted and it got stuck on the nickel strip. So why is it that one weld is very pathetic, whereas the other weld is very strong, right? We got the same welder, same setting, same aluminum and nickel strip. Let me tell you this story. That's one time I went for a job interview, and the first thing I did when I was in the interviewing room with the boss was to show him the two welds, right? One is very pathetic, the other one is a very strong weld. And he was surprised, and he asked me why I show him these two welds. I pulled right at the sign on the wall, and I told him, this is a $25 weld, and this one is a $35 weld. I'm just kidding, guys. If you look closely at this piece of aluminum, you will see that it has two shades. This part of the aluminum is very shiny, whereas this part here is very dull. And the dull part takes the weld really well. And I'll explain to you later in the video. Spoiler alert, this is not from sanding. The main reason why I want to spot weld to aluminum is because I have thousands of this Tesla Model 3 2170 cells salvaged from a Tesla Model 3, and the top of the cell is aluminum, and it's nearly impossible to spot weld anything onto the top of the cell. I've been working on this project for the last 4 years. I even have a notebook to document every single thing I have done. Yeah, I started in October 2022. And I have tried different things, different spot welder, different material, all kinds of stuff. And finally, I found out one method to crack the code. Here is all of the materials that I have gone through. I've got tin, titanium, steel, lead-free solder, zinc, tin, stainless steel, copper. This one is brass strip. I'm telling you, I've gone through the entire periodic table to find the answer. So in this video, I'm going to show you the best spot welder for this, and also the best material for this. So first of all, let's talk about the spot welders that you need. You're going to need a very powerful spot welder. On the right side, I have a Sunco 737 spot welder, and this spot welder is very pathetic. It can barely weld 0.15 millimeters nickel strip. I spent a lot of time with this spot welder with different materials, but it just did not work. I just didn't know why until I found this. This is a supercapacitor spot welder. Inside here there are two supercapacitors, 2.7 volts each, connected in series, so they're about 5.5 volts. This thing puts out over 2,000 amps. It is so powerful that every time I spot weld with this, the cable jumps, and it looks like this every time I spot weld it, if you pay attention. This is the spot welder that you need. It can weld up to 0.3 millimeter nickel strip. It can even weld a nickel strip on the top, copper strip on the bottom. Here you can see they are stuck together, and on the bottom here you can see it's all melted copper. It can completely penetrate both of this material easily. And it doesn't have to be this particular spot welder. There are many other supercapacitor spot welders on the market. There are also other transformer-based spot welder, like the Glitter 811H spot welder, but that thing is extremely expensive. It's like over $600. I don't have the money for that kind of spot welder, so a supercapacitor spot welder will do just fine. Here is all of the material I have for spot welding today, with the most conductive is from the left and the least conductive on the right. I've got copper, aluminum, nickel, tin, titanium, and stainless steel. Here's the table of conductivity I have for all of this material, with the copper being the most conductive, and on the bottom is a nichrome. I have rearranged the table to make it easier to understand. So these are all the materials I have over here, and let's assume copper conductivity is 100%, then aluminum is only 59% that of copper. Nickel is only 24% conductive compared to copper, and so on and so on. So as you can see on this table, copper and aluminum are the most conductive, and therefore they are not a very good candidate for spot welding, because when you spot weld, you need a metal that resists the current, and therefore will turn that into heat in order to melt and stick to your battery terminal. If it's too conductive, the current is just going to pass right through without heating up, and therefore it's not melting and it's not hot enough to stick to your battery terminal. This is the reason why nickel is the best candidate for this, because it's not very conductive compared to copper and aluminum, and therefore it resists the current enough to melt and stick to your battery terminal, and at the same time it's still conductive enough to be useful to carry enough current for your battery pack. All of the metal here below nickel, even though they are good candidates for spot welding because they resist the current, and therefore they are easy to melt, but they are not very useful in your battery pack because they can't carry a lot of current. It's time to do some welding. I got a piece of scrap aluminum here, and I'm going to try and weld these metal strips here on the aluminum. As you saw at the beginning of the video, this aluminum strip here, we got two parts. The part on the left side is glossy, which doesn't take the weld very well, and it doesn't stick. On the right side of the aluminum, you can see it's very dull, it looks different, and it takes the weld really well. You see how many welds I put on this part of the aluminum, and that's because I use this sodium hydroxide to clean up this part on the surface of the aluminum. And you can buy that at any local hardware store, and it's called heavy duty drain opener, which is just a fancy name for sodium hydroxide. And I'm going to use sodium hydroxide to clean up this part of my aluminum, and I'm going to smear it out evenly. Aluminum always has a thin oxide layer on the top, and that prevents from welding effectively. The reaction between sodium hydroxide and aluminum is a complex chemical reaction. It's actually 4 chemical reactions. The first reaction actually removes the aluminum oxide layer. Subsequent reaction exposes the pure aluminum so that you can weld more effectively. The end product is a release of hydrogen gas and 2 precipitate, aluminum hydroxide powder and sodium aluminate. These 2 precipitate, they are white powder. That's why you see this is turning white, and you can also see bubbles forming on the top, and that is hydrogen gas. And let me zoom in and show you clearly what is happening here. It's a lot of little bubble forming on the top, and this is turning white. That's because of the precipitate. So if I try to wipe it off, you see the white stuff is going away. I'm going to use isopropyl alcohol to clean off the rest of the residue. Now we end up with a part of the aluminum surface that looks pretty dull. It's no longer reflective. You can also use sandpaper to clean up the surface. I have tried sandpaper, but it's not as effective as using sodium hydroxide. Now we're ready to weld. I've got copper, aluminum, nickel, tin, titanium, and stainless steel. I'm not going to try copper and aluminum because they're too conductive. So when I put the probes on them, it's just going to be a dead short, and it's not going to weld effectively. I'm basically just shorting out my probes and the welder, and that's not very good for the welder. However, there's a trick to weld copper, and I'm going to show you later in the video. But for now, let's try from here down. Alright, we're ready to weld. Got some welds here because I did some test welds on it. But first up, nickel 0.1 mil. I set the welder to 0.2 milliseconds. Let's see what we got. It's stuck to my probe, but the weld is kind of weak. Well, let's increase it to 3 milliseconds. Alright. It's better, but doesn't stick very well. It makes a hole on a nickel strip. I believe this is too thin. So let's try 0.15 nickel strip at 3 milliseconds. See what we got. Not very well. I increase it to 2 pulses. So 3 milliseconds. And then the second pull is also 3 milliseconds. Let's try again at 4 milliseconds. Doesn't work very well, so let's try 0.2 nickel strip. 4 milliseconds. Now that is holding. Yep, that is holding. See if we can pull it out. Wow, I'm bending the aluminum. Keep in mind that aluminum is pretty weak. So there you go. That's a very good weld. Let's try again. Now let's increase it to 0.5 milliseconds. 2 pulses. One more. One more. All right, see what we got. Oh yeah, that's not coming out. Check that out. I'm bending the aluminum. Yep, that is strong. Strong for aluminum, that is. You have to keep in mind that aluminum is pretty weak compared to nickel. So when I rip this off, the aluminum comes off. But it goes all the way to the back. You can see that? It makes a hole all the way from the front to the back. So there you go. It works much better with 0.2 millimeter nickel strip because it's thicker, so it has more resistance, and therefore it has more time to heat up and melt to stick to the aluminum. So for nickel, a thicker nickel strip works best, preferably 0.2 millimeter. Next, let's try titanium 0.2 millimeter thick. Here we go. This 3 millisecond double pulse. Let's see what we got. Oh yeah, that's a good weld. Check that out. Let's see the back. Oh yeah, it penetrates toward the back also. Let's see, I can pull it out. Yep. See, I can bend the aluminum. Yep, that is pretty good for 3 milliseconds. I have increased to 5 millisecond double pulse. Oh yeah, I can feel the strength penetrate through the titanium. So let me reduce it down to 4. Reduce to 4 millisecond double pulse. Yeah, that's more like it. Let's try one more. One more. Okay, that's all we got. Let's see the back. Oh yeah, you can see the 5 millisecond, it makes a hole on the aluminum, and then the rest is 4 millisecond. It went through the back also. See how strong it is. That is strong. I'm bending the aluminum. Oh, it don't want to come out. Oh my. Yep, it's in there. Yeah. I can't pull it out. I'm deforming my aluminum plate. Oh my. Oh, that is strong. Wow. Okay. Wow, that is strong. So there you go. Titanium works much better than nickel. And that's because it's much less conductive and therefore has more resistance. So more time to heat up and melt and fuse with the aluminum. Next up is tin, 0.2 millimeter. Here we go. Tin power is 4 millisecond double pulse. Let's see what we got. Let's see toward the back. It does penetrate a little bit. See how strong the weld is. Not too strong. You need to increase the power. Here we go. Power is 5 millisecond double pulse. See the back. Yep, it penetrates to the back. How strong is the weld? Oh, not so strong. Here we go. 6 millisecond double pulse. Let's try one more. Alright. See the back. Oh yeah, it goes through the back. How strong is it? Not too strong. If you look at the weld, it penetrates and makes a hole through the tin strip, but it doesn't weld really well. So what that means is when it melts and it's trying to fuse with the aluminum, tin and aluminum doesn't make a very strong connection. It doesn't make a good alloy, that is. Next, let's try the stainless steel. This is on the bottom of the conductivity. It is 50 times less conductive than copper. Let's see what we got. Because it's thin, only 0.1 mil, I reduce the power to 2 millisecond single pulse. Not very well. You can see it makes a hole on the steel strip all the way through. What that means is we have enough power to penetrate the stainless steel strip, but because it's too thin, there's not enough time for it to heat up and melt and stick to the aluminum. What I have here is 0.26 millimeter stainless steel. This is very thick. For this one, I have not tried it before. I increase the power to 5 milliseconds, double pull. Let's see what we got. Oh yeah. Nope. Might be too thick. Well, actually, it's not too thick. It makes a hole through this stainless steel strip all the way through. So there is plenty of power to penetrate this, but it does not stick to aluminum. That means stainless steel doesn't make a good alloy with aluminum, so it doesn't stick. So previously I talked about spot welding copper onto aluminum, and the trick here is not spot welding the copper directly onto the aluminum. That's not going to work because copper is too conductive and there's not much resistance on the copper. The trick here is to use a piece of nickel, preferably a thin piece of nickel, 0.1 millimeter, put on top of the copper, and that will create resistance enough, hopefully, to create heat to melt the copper and also penetrate through the terminal underneath, the battery terminal, that is. Let me demonstrate. This is an 18650 battery. It has a carbon steel terminal on the top and also on the bottom. Let's try and see if this is going to work. We got nickel on the top, copper on the bottom, and the power is 5 millisecond double pulse. Seems to stick, and very well indeed. There we go. It looks like we need a little bit more power, so I increase it to 8 milliseconds double pulse. Yep, so that's a good weld. I can't pull it out. Yep, wow, that is strong. There we go. And it makes a hole on the copper and nickel. And the weld between the nickel and the copper is very strong also. I'm tearing off the copper. So is this combination going to work with aluminum? There's only one way to find out. Here we go. Nope, it doesn't stick very well. Came right off. This doesn't work because copper doesn't form a very good bond with aluminum. Its alloy is pretty weak and therefore it doesn't stick very well. But we know that nickel forms a very good bond with aluminum. The alloy between nickel and aluminum is very strong. So what I'm going to do is I'm going to sandwich the copper strip right in the middle between two nickel strips. Each one is 0.1 millimeter. So the total thickness is 0.3 millimeter. I'm going to increase the power on my spot welder to 17 milliseconds out of 20 and double pulls. So that's about 85% power. So here we go. Nickel, copper, and then nickel. 3 layers. Here we go. Yep, I can feel the power from the probe. But it doesn't stick. So either I don't have enough power or my strips are too thick. Let's try this again with a thinner piece of copper. This one is 0.07 millimeter. Here we go. Let's see what we got. Yep. That is, I would say, not very good, but it's actually sticked. I just increased the power to 18 milliseconds. That's 90%. See what we got. Let's see, we penetrate the bottom. Yes, we did. Yep. There's a hole, there's two holes on the aluminum. See how strong this is. Oh yeah, that is strong. I'm bending the aluminum up. That is strong. So yes, you have to keep in mind that aluminum is pretty weak. Therefore, it gives way first before the nickel. But for aluminum, that is a strong weld. Let's try this again. All right, 3 welds. Let's look at the bottom. Yep, you can see the 3 welds here. Penetrate through the aluminum. Yeah, that is strong. I'm lifting up the aluminum. And yes, there's a hole that goes through the aluminum. So that is strong. That's a strong weld. So by putting the copper in between the nickel strips, I have increased the current carrying capacity of this conductor. And because copper is almost twice as conductive as aluminum, this is total thickness of this is less than 0.3 millimeter, but is equivalent to about 0.4 millimeter thick nickel strip. And that is something beyond the power of this welder. So this is basically like a cheat code for spot welding. Now let's try on the battery. This is a Tesla Model 3 2170 cell. The positive terminal is aluminum. First, we need to clean it up with sodium hydroxide. There's a lot of bubble forming and it's turning white. Let me show you the secret of welding a Tesla 2170 cell. This is a cell that is burnt off. It's being shorted out and it pops up the top aluminum terminal here. If you look underneath the aluminum terminal, you see 3 concentric circles, right? 1, 2, and 3. And they are different thickness. The outer layer is 0.2 millimeter thick. This circle here in the middle is 0.5 millimeter thick. And the one that is right at the center here, the little circle, is about 0.8 millimeter thick. And this is where, right at the center, they weld the fuse wire right on the center, the original cell, that is. So they actually weld the fuse wire right at the part where it's the thickest of this aluminum terminal. So when we weld on a Tesla cell like this, we have to keep right on this circle here. This is about a centimeter in diameter, and this is 0.5 millimeter thick. The outer ring on the outside of this circle is only 0.2 millimeter. So you have to be careful, otherwise if you weld it on the outer ring, this ring, you might punch a hole through the cell, and that's dangerous. So you want to keep it within this circle here. You can certainly weld it on the outer ring, like this ring here, from here to here, but you need to keep the power down to prevent it from going through the aluminum. I got the battery ready, and because it's a bare cell, I'm going to put some insulation on. Here we go. Power is at 8 millisecond double pulse. Let's try and weld one more. Looks like a pretty good weld. Yep. So that is holding good. At 8 milliseconds, it might be a bit too much. So I might have to reduce it down to 6, but the weld is solid. Nice and solid weld. Let's try one more. This time is at 6 milliseconds. I realized I didn't push it down enough, so it penetrates too much through the nickel strip, but it is, however, still a good weld. If you take a look at the Tesla cell, unlike any other battery, the top of the cell is kind of concave downward, whereas other battery is completely flat, so it's easier to weld. This is concaving downward, so when you weld, you have to really push down on the nickel strip for it to have a good contact with the aluminum surface. I'm trying to weld these two cells together in parallel, so let's try this again. This time I'm trying to push it down to make sure it's flat on the aluminum surface. Here we go. I reduce it down to 5 milliseconds, double pulse. Looks pretty good. Let's do one more. That looks good. Let's try one more. Oh yeah. This looks better than the other side, so I would say 5 milliseconds is best. The other side, which is the negative side of the battery, is made of carbon steel, so it's a piece of cake to weld this. Here we go. See how strong that is. Yeah, that is strong. Beautiful weld. So next, let's try this pouch cell from an EV battery. It's made by LG, 53 amp hour, and I'm cleaning it up with sodium hydroxide. This aluminum is very thin. It's only 0.2 millimeter. Let's try it on a 0.2 mil nickel strip. I'll reduce the power to 3 milliseconds, double pull. Wow, looks like too much here. Punch a couple of holes from one side to the other. Because this aluminum is way too thin, I'm going to try and see if I can sandwich a piece of nickel strip on the bottom. So let's try this again. We got 0.2 nickel on the top, and then the aluminum, and then we got 0.1 nickel on the bottom. Here we go. 0.3 milliseconds, double pulls. Oh, it doesn't stick the bottom part, but it does stick on the aluminum. See the other side. Looks good on the other side. It penetrates the other side. See how good the weld is. Yeah, I'd say that's holding. That's holding. Let's try a couple more welds. See what we got. Okay, so it doesn't stick to the bottom nickel strip. But the weld is solid. Check that out. Here is the bottom, and you can see melted aluminum on the bottom here. So it penetrates all the way through. So for batteries like this with skinny aluminum terminal, putting a nickel strip on the bottom to absorb the heat helps it weld much better. So how strong is this bond? I'm bending the aluminum. Yep. Whew. Yep, it's holding pretty good. That is holding pretty good for a 0.2 millimeter aluminum tab. So there you have it, how to spot weld batteries with aluminum terminal. Of all the metals I have tested, nickel comes out on top, specifically 0.2 millimeter thick. Titanium is the next best thing. However, titanium conductivity is only 4, nickel is 24, so it's only about 1/6 the conductivity compared to nickel, or about 17%. Because you're going to have to use a very thick conductor, 6 times as thick compared to nickel, to carry the same amount of current. I also try aluminum on aluminum, but what I have is only 0.1 millimeter, and that's too thin. It just blow a hole right through my aluminum strip, so that didn't work. Working with aluminum is extremely difficult. I have looked all over the internet before I started this project 4 years ago. I couldn't find anything, even until now. Now I have a chance to use my thousands of Tesla Model 3 2170 cells, which I didn't know how to use it before. The Tesla 4680 cell battery terminal on the top is also aluminum. Any comments or ideas to make this better, please write down below, because that might help a lot of other people. And that's all I have for now, folks. Thanks for watching, and I will see you in the next video.